It's true here at Spindletop, just like anywhere else, that there must be three criteria for the formation of important gas and oil deposits. First of all, you have to have a source rock. A source rock is an organic-rich sedimentary rock which, when buried deep below the surface of the ground, has the organic matter transformed by heat into gas and oil. Secondly, you have to have a reservoir rock, which has considerable amount of porosity. This rock has voids or pore spaces in it, fractures, spaces between grains, or solution holes, which can hold the gas and oil. And thirdly, you have to have a trap, or a high point on the reservoir rock. The gas and the oil then congregates by buoyancy in the trap. Let's take a close look at all three of these important criteria. No matter what environment you can think of in which sediments are being deposited, there's always a lot of organic matter being deposited right along with the sediments. Look at this. Dead vegetation, dead animal matter being deposited right along with the mineral grains. There's an enormous amount of organic matter in ancient sedimentary rocks. This black shale is very rich in organic material, and heat will transform organic material into gas and oil. As you go down in the earth, it becomes hotter and hotter. From the surface of the earth down to about 150 degrees Fahrenheit, only bacteria works on this organic material to produce methane gas. But after you reach about 150 degrees Fahrenheit, temperature takes over and turns the organic material into oil. Heavy oil is produced at very shallow depths, from about 150 degrees Fahrenheit down, and light oil at the deeper depths and higher temperatures down to about 300 degrees Fahrenheit. This is called the oil window. Below 300 degrees Fahrenheit, the oil is broken down into gas, and oil cannot occur below 300 degrees Fahrenheit. This black shale is thought to be the source rock for much of our gas and oil. Look at this. This river is depositing a long, narrow sand body. And if this is buried in the subsurface, it'll become a long, narrow sandstone. This is a good example of one of those ancient, long, narrow sandstone bodies. This was deposited over 100 million years ago and was buried deep below the surface of the ground. Today it's been exposed by erosion, and we can see the rock outcrop here in this road construction. You can envision how hard it would be to drill to something like this, 5 or 10,000 feet below the surface of the ground. If you take a look at it, it's very, very long and narrow, and that's why we call it a shoestring sandstone. And this is another type of important gas and oil trap. This is a typical reservoir rock, limestone. And it can form an oil trap. But in order to have an oil or gas trap, on top of the reservoir rock, you must have a seal to prevent the gas and oil from leaking up to the surface. And over here we have a perfect seal. This is shale rock. It's impermeable to the gas and oil and prevents it from leaking up toward the surface. Shale or salt make excellent seals or cap rocks to these reservoirs. What happens in a reservoir deep below the surface of the ground? The gas, oil, and water separate out according to buoyancy. In a reservoir, you'll find the free gas cap on the top. Underneath that, the oil, and underneath that, the water. They form level surfaces, which are called the gas-oil surface and the oil-water contact. If we were to drill right on top of the structure, we'd encounter primarily gas. Farther off the structure would be oil. And if we were too far off structure, we would have just water. which interestingly enough is called a dry hole.
There are two important techniques for exploring for petroleum. First of all, there's seismic exploration, and secondly, subsurface mapping. This is a seismic profile. This is like a cross-section going down into the ground. This is the surface of the ground, and this is down into the ground. Because this is an offshore profile, this is the surface of the ocean right here, and this is the bottom of the ocean that you see here. The lines that you see here are reflections off subsurface layers. Layers such as sandstones, limestones, and shales. You can see the subsurface structure from these seismic profiles. Using VibraSeis, you drive a special truck into the area, and the truck vibrates the ground hydraulically. This puts sound down to the ground, which reflect off subsurface rock layers. These echoes are then recorded on the surface of the ground. This gives us an idea of what the subsurface structure is like. If other wells have been drilled in the area, then we can get some information about the subsurface rocks from those wells. We can make what is called a well log. One of the most common methods of well logging is to call in a service company, which will drive to the well with the truck and lower an instrument down the well, which is called a sonde. This instrument, the sonde, is then raised in the well, and it senses the properties of the surrounding rocks, such as electrical or radioactive. It produces what we call a well log. This is what a well log looks like. It's a long strip of paper that records the rock properties as you go down into the earth. A typical well log has a depth below the drilling platform in the center of the log. And then on either side it has curves which record the properties of rocks as you go down into the earth. These properties could be electrical or radioactive. Then, if you take a look, at the very top of the log, you'll see all sorts of information about where the well is located and when the logging was done. A good method of obtaining information is by taking a core. This is a core, a cylinder of rock drilled from the well. From a core such as this, we can obtain the most accurate information as to the porosity, permeability, and even the saturation of the reservoir rock. How do we take a core? When we're ready to take a core, we pull all the pipe out of the hole. We then change the drilling bit for a special coring bit. This is then lowered down into the hole, and the coring bit cuts in a circle, leaving the core in the center. This is then pulled to the surface, and then we resume drilling. As you might suspect, this takes time, and time is money on a drilling rig. So we just don't core everything. We core only when we want accurate information as to the properties of the reservoir rock. Let's say that this is a three-dimensional representation of the Osage Hills, and this is the area in which we took that core. An important aspect of exploring for petroleum is subsurface mapping. How do we take a three-dimensional feature, such as the topography of the Earth's surface, and show it on a two-dimensional map? We use what are called contours. Contours are lines of equal elevation, and this is a typical topographic map that shows us the elevation of the Earth's surface. This is the map that we see for the Osage Hills. These contours show us the elevation of various points on this map. It shows us high and low areas. But geologists are most interested in subsurface formations, and therefore we have two special maps which we use, which are called structural maps and isopack maps.